we spent 3 lectures discussing 4-dimensional dynamics. So in the first lecture, we developed the tools to discuss 4-dimensional n=1 supersymmetric RG flows. And in the last 2 lectures, we discussed the dynamics, mainly in the last lecture. We saw very interesting effects of emergence of symmetry, IR dualities, and so on. And I will start today with the last slide or last page that I have shown you last time, yesterday. And we will today try to understand how one can embed these interesting dynamics in 4 dimensions in a bigger setup, in a geometric setup. So we will add degrees of freedom. We will add levers and knobs. And we will see how this additional stuff helps us to understand the 4-dimensional dynamics. So last lecture and the lecture before that were very technical. This lecture will be much less technical, simply because I will not have enough time to develop all the technicalities. In the notes, if you are interested in all the technical details, you can find the technical details. They will be they contain much more technical information. So we will start this talk from some general geometric considerations, and what you can say from geometry will develop certain understandings. Again, this won't be too technical, but at least I want you to understand the basic ideas behind this geometrical engineering. And then in the second part of the talk, we will see how various dynamical effects that we have seen in the last lectures appear in this geometric setup. So we will make a connection to exactly the dynamics that we have discussed in last lectures. So again, let me repeat the general idea that I have already discussed in the last minutes of yesterday's talk. So again, we have this, we understood a lot of these interesting dynamical phenomena in 4 dimensions. We understood that these phenomena exist. And what we are after is some guiding principle, how to understand and how to classify such phenomena. And the idea that we will explore is to embed these 4-dimensional theories into a 6-dimensional setup. Okay, so we will start from a 6-dimensional supersymmetric theories, superconformal theories. There are a huge variety of 6-dimensional superconformal theories, which are called 1,0 theories and 2,0 theories. Okay, I will not discuss the details of what these words mean and so on, but it's important to know that these theories exist. And there is a lot of research in trying to classify them and understand them. And I believe Sakura will discuss some aspects of this research. And then we take some 6-dimensional theory, any theory that you want, and we put it on a compact Riemann surface, okay, and flow to low energies, far below the energy scale set by the surface, where we get effectively a 4-dimensional theory. And again, as in 4 dimensions, in the end of the flow, this theory might be gapped, might have free fields, free gauge fields, or might be a strongly interacting SCFT in 4 dimensions. Okay. Again, we will repeat it over and over again. We'll do this deformation in such a way that we preserve supersymmetry and we preserve Samar symmetry. It is very important because this gives us control. In principle, we can, as always, discuss these types of flows without supersymmetry, but we will insist on having supersymmetry. So we end up with some theory in 4 dimensions. And then one interesting question that we will ask, is there a 4-dimensional theory that we can construct using fields and chiral fields and gauge fields, and which flows directly to this SCFT in 4 dimensions, or in more generalities, and this QFT. In particular, today, we will not just discuss RG flows, which will flow to these CFTs, but we will have 2 examples of theories which will describe exactly this fixed point. So we will find a conformal dual, if you wish, of this flow directly in 4 dimensions. So when I say RG flow, the RG flow might be trivial in the sense that we don't flow, we directly describe the same SCFT. So by this logic, you can see that there are a lot of choices that you can make starting from 6 dimensions. You have a choice of the 6-dimensional theory, you have a choice of the Riemann surface. And all these various choices give you different theories in 4 dimensions. So I denote here by T4D the theory in 4 dimensions, and it is defined by your choice of 6-dimensional original theory and the Riemann surface, the compact space on which you compactify. So this is the choice of geometry, and this is the choice of the 6-dimensional theories. And the properties of these 4-dimensional theories will be encoded in these 2 choices, in the choices of the 6D theory and the choice of geometry. And this fact that there is a geometry hidden in the definition of this 4-dimensional theory will play an important role, as we will see. Okay, so we have this flow. So as in 4-dimensional flows, we need to develop or understand certain techniques, certain tools, which will help us understand what can we say actually about this fixed point. So we start with these 6-dimensional theories. We flow again. Well, here the story is much more complicated in 4D, since these 6-dimensional theories by themselves are strongly coupled, and we have only very, in a sense, indirect definitions of these theories. So on top of that, who knows what happens during the flow? But we need certain tools to understand what can we actually say about the fixed point, exactly as we had in 4 dimensions. And the things that we can say are very similar to the things that we could say in 4 dimensions. For example, one such RG invariant information, and here again, the RG that we have is across dimension, is 't-Hooft anomalies for various symmetries that we have. Okay. Here, however, there is a problem. In 4 dimensions, we had a theory in 4 dimensions. We've flown to a theory in 4 dimensions, and we had a 4D anomaly polynomial in UV and in the IR. It should have been the same. Here we start from a 6D theory, which has a 8-form 6-dimensional anomaly polynomial, and we end up with a 4-dimensional theory, which has a 6-form anomaly polynomial. So we need to, in some way, to be able to relate these 2 anomaly polynomials. And the relation is very simple, okay? So if you start from a 6D theory, and you know it's anomaly polynomial, okay, there is some way to compute it. And for different 6D SCFTs, there are various techniques that were developed to compute this anomaly polynomial. We will assume that this was done. And again, in the notes, there is one example of derivation of such an anomaly polynomial very explicitly. And you have the surface on which you compactify. In addition to choosing the surface, if the theory has some global symmetry, you can turn on background fields for this global symmetry. You can turn on some non-trivial bundles on this Riemann surface. So the way to get the anomaly polynomial of the 4D theory that you obtain in such a compactification is just to take your anomaly polynomial of the 6D theory and integrate it over the Riemann surface on which you compactify in presence of these non-trivial bundles or fluxes, if you wish, for the global symmetry. Okay. This integration over this 2-dimensional space will produce, will take this 8-form anomaly polynomial and produce for you a 6-form anomaly polynomial, which will be the the anomaly polynomial of the 4-dimensional theory. Okay, and the logic, the intuition is very simple. Again, we have this theory in 6 dimensions. We put on a Riemann surface and we kind of integrate out the degrees of freedom that live on the surface and flow to low energy, which is a 4-dimensional theory. Okay. Again, we will insist that in this procedure of compactification, we preserve supersymmetry and we preserve some R symmetry, which will be very important for us. Okay. The meaning of preserving supersymmetry is as follows. If you put your 6-dimensional theory on a Riemann surface, on a higher genus Riemann surface, it's a curved background. And because it's a curved background, naively you break all the supersymmetry. Okay? So you need to take care that, do something so that some supersymmetry will be preserved. And this procedure of preserving supersymmetry is called twisting. Basically, supercharges transform both under Lorentz symmetry and under certain R symmetry, So you turn on some non-trivial background for this R symmetry, such that it will cancel the effect of geometry, and at least some of the supercharges will be preserved. The minimal amount of supersymmetry these 6D theories have is 8 supercharges, and there is a way to do this twisting procedure to preserve 4 supercharges, which is n equal 1 supersymmetry in 4 dimensions. Okay, so we assume that we do that. Okay, we turn on those types of backgrounds for R symmetry, which preserve 4-dimensional n equal 1 supersymmetry. On a torus, which is flat, you can preserve all the supersymmetry in principle. But we will not concentrate on a torus. As we said in the beginning, we will only discuss things which are more generic, which are true for n equal 1 and not just n equal 2. Okay, so there are a couple of comments that I want to make before discussing the next Argin variant information that we can deduce. It is important to know, although it will not have a direct implication for what we will say, that the 6D SCFTs don't have any continuous parameters. This is very different from the 4D SCFTs that we have discussed that could have had conformal manifolds, spaces of couplings that you can tune. The 6D theories don't have such couplings. On the other hand, as I just said, the 4D theories can have parameters, so you can ask where the parameters, the couplings of the 4D theory come from. And these parameters come from various geometric sources, as we will now discuss. And for example, the surfaces on which you compactify can have parameters, the so-called complex structure moduli. And we also, if we have global symmetries, we can turn on flat connections around various cycles of the Riemann surface. So next thing I want to discuss is, okay, we understood the anomaly, or we discussed how to predict 't Hooft anomalies of various symmetries in 4 dimensions by integrating the anomaly polynomial. What about, is there an analog of matching the indices, some information, some protected information about operators in the 4-dimensional theory? So here, there are certain things that you can say. The technology of predicting the spectrum of operators starting from 6 dimensions is not as developed as one would have hoped, although in principle, one can do more than I will say here. But the logic is as follows. Say you have some supersymmetric, some protected operator in 4 dimensions. You can ask yourself, now I compactify this theory on a surface. What type of operators this protected operator in 6 dimensions gives me in 4 dimensions? So in a sense, the question is, what is the KK reduction of a given operator starting from 6 dimensions down to 4 dimensions? So again, I will tell you the story in a bit of a pictures. A way to proceed is to try, you have this Riemann surface, this compact space, and you have this local operator, so you can try to smear this operator on this Riemann surface. And there are various ways to do so, preserving supersymmetry so that the local operator that you will get in 4 dimensions will be protected. So there are certain natural local operators in 4 dimensions, for example, the stress energy tensor. And doing so, smearing the stress energy tensor or components on it on Riemann surface, one can show that this gives rise to 3G minus 3 exactly marginal operators in 4 dimensions. Okay, and these are exactly the ones which corresponds to this complex structure moduli that I mentioned. Another thing that you can do is if your 6D theory has a conserved current, you can again try to ask yourself, okay, I compactify this operator to 4 dimensions, what can I get? And what you discover is that if you don't turn on any flux on the surface, so if there is no flux, you don't break your 6D symmetry by turning on flux, you will get a certain number of exactly marginal operators in 4 dimensions, and this number is equal to the dimension of the 6D group times G minus 1. You can ask, how do I know that these operators will be exactly marginal? Well, we know that these exactly marginal operators have certain quantum numbers. Okay, they, for example, have certain R charge and so on. So these operators that we get in this procedure have the right quantum numbers to be exactly marginal operators. And in this case, you don't get, in the case that there is no flux, you don't turn on flux, you don't get any relevant operators from these two very generic operators that you have in 6D. In case you do turn on flux, the story is much richer. The number of marginal operators is related to the group which is not broken by the choice of the flux. So again, the flux is just choice of some classical background that you put on this Riemann surface, and you explicitly break your 6D global symmetry to some subgroup. So the marginal operators will be related to the unbroken group, if you wish, and you will have also a plethora of some relevant operators, which will be related to which can be determined in terms of what is exactly the value of flux, how the group is broken by the value of flux, and so on. Okay. So this is the story. Yes.
Can I ask a question?
Sure.
So is that all the relevant operators come in this way?
So this is the next page. Thank you for the question. So these are the generic operators, okay, that you would obtain. So with a generic compactification, say high genus, generic value of flux, this will be all the operators. Okay. But there are caveats, and this is, well, okay, let me first say the caveats, and then I will go to the top of the page. So, of course, there can be, for a given compactification, there can be some other, operators that your 6D theory has, which will give you, in 4 dimensions, relevant operators. Relevant operators, for example, are operators with low R charge. Okay, so kind of intuitively, you should start from some operators with low charges in 6 dimensions to produce low charges in 4 dimensions. So in general, the stress energy tensor and the conserved current will be the only such operators. But for specific cases, other operators can contribute. Another caveat is that I have discussed only compactification of local operators by smearing them on the surface, but also non-local operators in 6D can give you rise to local operators in 4D. Okay? So you can take certain surface defect, wrap it on a surface, and then obtain a local operators in 4 dimensions. And it might be that it will give a relevant operator. Again, the intuition is if the charges of this, as you have a higher and higher genus surface, when you wrap this surface operator on higher genus surface, I don't know, vague intuition is that its charges should grow with the genus. Okay, so for generic genus, this surface operator should not contribute. Okay, but for low genus, they might contribute. And again, this fact that non-local operators in higher dimensions give rise to local operators in lower dimensions is, of course, very well known. For example, if you start from 4D and compactify on a circle, then line operators can become, these are the things which become monopole operators in 3 dimensions. Okay. Does this answer your question, Jema?
Yes, thank you.
Okay. Okay. So let me say also a couple of comments about the symmetry. So we said we can predict at least certain operators. And again, in principle, if one is powerful enough and one can compute the partition function of the 6D theory on, let me write it here, on say S3 times S1 times this Riemann surface sigma, okay, then one can just send the size of this sigma to be small and take certain limit of this partition function and deduce the supersymmetric index of the 4-dimensional theory. So there are certain works to that end, but I would say till now this possibility exploration of such partition functions was not completely explored. If we would have very good technology of doing these types of partition functions, these arguments which are just following certain operators would not be necessary. As in 4 dimensions, we would just follow these supersymmetric indices of various types. Okay. Again, I'm not saying this cannot be done, but this technology was not completely fully developed at the moment. So what else can we say? And as in as in 4 dimensions, we can ask ourselves what happens with the symmetry. And well, if we have a some symmetry in 6 dimensions, as I already mentioned, since we maybe turn on some flux on the Riemann surface, we preserve some fraction of this of this 6-dimensional symmetry. So naively, the 6-dimensional symmetry which is preserved is the symmetry which commutes with the choice of flux. Okay. In addition, these marginal operators that we have discussed, they in principle break. They are in a joint representation of the preserved symmetry, and they parameterize some conformal manifold. And when we go on this conformal manifold, these symmetries are broken. So generically, we preserve some subgroup of this 6-dimensional group in 4 dimensions. And here are these caveats that we also mentioned when discussing 4D flows. There might be some emergent symmetries in the infrared, which is in 4 dimensions in this case. And there might be some symmetries which don't act faithfully. Okay. So in principle, there might be a situation where we preserve certain symmetry, but there is nothing charged under it in 4 dimensions. Okay. So as in 4 dimensions, these things in principle can happen. And this is also related to J1's question. You can ask, okay, you using this KK reduction of operators, you predict that certain operator exists there. There is a conserved current. You know, how can it disappear? Well, it disappears because in the RG flow, it might be recombined with something, some other operator which comes from some other source, and so on. And in the end of the day, you know, you don't have a conserved current, although you did not break it explicitly. So these are all caveats that are important to remember when discussing these flows. Okay, so let me give you an example of what kind of a thing one can do. So I will give you 2 examples in these lectures. Again, and I choose these examples because they're extremely simple and they relate to the very explicit 4-dimensional discussion that we had in previous lectures. So we make here a choice of 6-dimensional theory, which is called the minimal SCFT, which is associated to a group SU3 in 6 dimensions. Okay, I believe Sakura will discuss it at some point in her lectures, but just let me mention that, you know, this is some strongly coupled SCFT, which doesn't have any global symmetry, any continuous global symmetry. It has a certain Z2 global symmetry. A lot of things are known about this theory. For example, the anomaly polynomial can be computed. And in the notes, I write down in detail how to compute the anomaly polynomial of this theory. This theory is very simple. The 6D theories have something which is called the tensor branch. And on a tensor branch, this theory has an explicit description and as an SU3 gauge theory coupled to some tensor multiplier. So it's an extremely simple theory, and you can compute many things about it. Okay, so now we can just do what I said on the previous slide, and for example, we can compactify on a Riemann surface. Here we don't have any global symmetry, so there is no issue of turning on fluxes. The only thing we can choose is choose the Riemann surface. And we can integrate the anomaly polynomial of the 6D theory on the Riemann surface and produce an anomaly polynomial of the 4D theory. And these are the conformal anomalies that you would get by doing so. Okay, so there is a prediction here. Start with this particular 6D SCFT, compactify on a Riemann surface. You find quantum field theories in 4 dimensions, which have these particular A and C anomalies, which depend on a genus G of your Riemann surface that you have chosen. Okay, so in this picture that we have here, we started with this SU3 minimal SCFT in 6 dimensions. We chose its surface, we compactified it down to here, and we know what the A and C anomalies of the resulting theory should be. Okay, so now the question is, can we find such a theory in 4 dimensions? Can we describe such a theory with these types of anomalies and other properties that we'll discuss directly in 4 dimensions? Before we do that, it's commonplace to call such a theory non-Lagrangian. Okay, for a general compactification that you will perform with a general choice of 6-dimensional theory, you will not know what type of a 4D theory explicitly describes that type of compactification, and it is common to call these theories non-Lagrangian. I don't like this name, so this will be the only place I will mention it, and let me just wipe it out. Okay, and in this case, we will actually find the Lagrangian, and in the end, I will make a certain conjecture to this end. Okay, so now what can we do? Again, we can do exactly what follow the logic that we had in 4 dimensions. So we have this geometric prediction that there is a theory. Okay, this theory has a conformal manifold, a 3G minus 3-dimensional conformal manifold, because this theory in 6 dimensions has a stress energy tensor. So when we compactify on a Riemann surface, we generically would expect a 3G minus 3-dimensional conformal manifold. It doesn't have any global symmetry. Okay, and we know it's A and C anomaly. So we can ask ourselves, is there a point on this conformal manifold where there is another description? Okay, for example, in terms of a conformal gauge theory. Okay, in an example that we did in the last lecture, we had a G2 gauge theory, SQCD, and we looked for another gauge theory description. Here we have a definition of a theory which is very indirect. It's very abstract. We start from 6 dimensions, we get some theory, we know some information about this theory, and we want to find a conformal dual for this theory. It might exist or might not exist. Of course, I give you this example here because there is such a dual, but in general, it's not guaranteed. And in fact, in generic compactification that you can consider, you can show that a conformal Lagrangian does not exist. How you show that? Okay, so again, exactly as we did in the previous lecture, the A and C anomaly, under the assumption that there is a dual conformal gauge theory description, predict what is the dimension of the gauge group and what is the dimension of the representation of that putative gauge theory. In this particular case, with these anomalies, you can solve for this dimension of the gauge group and dimension of representation and find that these numbers are integer. Okay, it's 32 times G minus 1 is the dimension of the gauge group, 81 times G minus 1 is the dimension of the representation. For generic compactifications, if you do this kind of game, you find fractional numbers. So you immediately rule out such a conformal dual. But here you get integers, so there might be a conformal dual. And indeed, we will find it. And again, 32 is a nice number. It's 4 times 8, and we will see that it will actually correspond to 4 factors of SU3. So for genus G compactification, we will have 4G minus 4 SU3 gauge group, a gauge theory with this 4G minus 4 SU3 gauge groups and certain collection of chiral superfields. Okay. This is first example that we will discuss, and here is the second example. And second example is what is called rank 1 E-string theory, and I understand that Sakura already yesterday has discussed this theory. So again, this is some 6D SCFT, for which we know a lot of things. We know the 6D anomaly polynomial. It's more complicated to compute than the anomaly polynomial of the theory I mentioned before, but it's possible to do so, and by now it was done in different ways. And another interesting fact about this theory is that it has a very interesting symmetry. It has an E8 symmetry, okay? Unlike the theory that we mentioned before, which didn't have any continuous symmetry, this has an E8 symmetry. So when compactifying, we can turn on also fluxes for this E8 symmetry. But for now, let me not turn on any fluxes. Just again, as we did for the minimal SU3 theory, we compactify on a genus G Riemann surface without fluxes. And again, we can predict anomalies. And again, we can ask what happens is there a description in 4 dimensions, directly in 4 dimensions of this theory? Here again, as we have a global symmetry, we can also ask what is the 't Hooft anomaly for this global symmetry. And again, also from the same anomaly polynomial, we can compute this 't Hooft anomaly, and it will depend on a genus. And that's the value that you will obtain. And well, remember the simple answer, it will come again later on. Okay, so we will ask the same question as in the first example. We find a theory which has a conformal manifold. Here, the conformal manifold is much bigger. It has 3G minus 3 dimensions, which come from stress energy tensor, but it also has 248 times G minus 1 dimensions, which come from the conserved current. It is some n equal 1 supersymmetric quantum field theory. On a generic point of this conformal manifold, all the symmetry will be broken. It's easy to show using the same techniques that we used before. Since the marginal operators are in the joint of the group, we can break this group going on a generic direction of this conformal manifold. And again, I mentioned this fact that where the E8 is preserved, its 't Hooft anomaly is given by this value. So again, we can ask: is there a gauge theory description of this theory somewhere on its conformal manifold? We solve this simple set of linear equations, and again we find that the dimension of the group is integer. It's 16 times G minus 1, and actually for representation we can find exactly the same answer as for minimal SU3 theory, 81 times G minus 1. So it might be that there is a conformal gauge theory description. We need to look for it. If these numbers would have been not integer, this would rule out this possibility. Okay. So before going and telling you what actually these theories are in 4 dimensions, how to construct them, there is another kind of very generic statement that I want to tell you. So we are discussing till now compactifications on Riemann surfaces, which are closed with no punctures. They have only some genus, but no holes in them. But you can actually discuss the same types of compactifications when your Riemann surface has some marked points, some punctures, okay, or holes. And actually, it is very useful to do so, as we will see in a little bit. So how can you think about the puncture? So one way to think about them, you can take your favorite Riemann surface and just cut it along a certain tube and then produce, say, 2 surfaces with a puncture. So what is a puncture? Again, a puncture is a hole in the Riemann surface. And in this compactification business, it just means that you have a space-time with a boundary. So we have a quantum field theory and a space with a boundary. You need to specify in some way the boundary conditions for various fields on that boundary. Now, in 6 dimensions, we don't have a very useful description in terms of fields of the corresponding theories. So it's a question which is rather hard to answer, what a puncture means in 6 dimensions. There are ways to address it, but I will not go into it here. But there is a very nice trick or nice way to understand what a puncture is. And the trick is that we can think of the region near the puncture as some kind of a cylinder. Okay, so instead of compactifying on a 2-dimensional surface, we first compactify on 1-dimensional circle and go first to 5 dimensions. Okay, and by going to 5 dimensions, we can turn on various holonomies around the circle and scale them with the radius. And it so happens that if you do this thing, you go to 5 dimensions on a circle with proper holonomies. In some cases, what you find a 5-dimensional theory, but not just any 5-dimensional theory, but a theory which has an effective description in terms of a gauge theory in 5 dimensions. This gauge theory might not be UV complete in 5 dimensions. It might be UV completed in 6 dimensions. But it is an effective description. Why is it important? Now we have a description of the theory on a circle in terms of fields. So now we can understand what are boundary conditions that we can define for those fields. And in this way, define the punctures. So in this way of going from 6D to 4D in this geometrical engineering, there are various moving parts that you need to understand. So you need to understand well the 6D theory, say you compute the anomaly polynomial. And also the compactification to 5 dimensions will turn out to be very important. All of these moving parts are hard questions to answer, hard to address, and there is a lot of research going into it. Again, this story of going to 5 dimensions from 6 dimensions is exactly part of what Sakura will cover in her lectures. Okay. So what is the story for our two examples in this respect? So if you take this minimal SU3 SCFT, I mentioned that this theory has some Z2 global symmetry. If you twist with that Z2 symmetry, you can show that the effective theory that you find in 5 dimensions is pure SU3 gauge theory with some Chern-Simons level, Chern-Simons level 9. Okay. The fact that you get an SU3 here and SU3 here, it's not trivially related, just as a side comment, but it so happens here. Okay, so this is the 5D theory that you get, and now you can put a boundary and ask yourself, what are the supersymmetry preserving boundary conditions that you can have? And there is a certain boundary condition which is called the maximal boundary condition, which is very nice. In this boundary condition, you take these gauge fields, 5-dimensional gauge fields, and give them a Dirichlet boundary condition on the boundary, on this puncture. Okay, and whatever supersymmetry tells you to do for other fields, you do for other fields. Okay. Now, what is happening with this boundary condition? Since you have this Dirichlet boundary condition, you can think of this 5D gauge symmetry as being frozen on the boundary. So what you effectively have done, you have produced a global symmetry, an additional factor of global symmetry, which is associated to each one of the punctures. If you have many punctures, you can do it for every puncture. And this global symmetry is the 5D gauge symmetry. So it's SU3 global symmetry for each puncture. Okay. And the ones, if you have followed the class S story, where you compactify a 2,0 theory and so on, this is exactly the same story. This is a very general statement that one can have. Now, in addition to having these SU3 symmetries, you can compute the anomalies of the 4D theories resulting in compactification on the surface, on the boundary, on a surface with punctures. So anomalies have two sources. They have a geometric source. So we had an anomaly contribution here on a closed Riemann surface, which depended on this G-1. If we have punctures, the geometric source will just be the same. We just trade G-1 with G-1 plus S2 with the Euler characteristic. However, there are additional contributions to these anomalies coming from the puncture, from the inflow arguments at the punctures. And again, if you want this more details on how this exactly works, you can see in the notes. The end result, when you add this inflow from the various fields that you have in 5 dimensions on the boundary and this geometrical contribution, you will get such anomalies for this compactification. In addition, you have these global symmetry factors associated to the punctures, and again, from the inflow arguments, you can compute the anomalies, the 't Hooft anomalies of these puncture symmetries with the R symmetry and the cubic anomaly of this SU3 symmetry. This comes from the Chern-Simons term that this theory has, and this comes from the gauginess in the vector multiplet. Okay. This is the story for example 1. For example 2, it's very similar story. Here we start from E-string theory, and instead of twisting with Z2, we turn on certain holonomies which break.
Shlomo,
yes.
What was the sign in front of the cubic anomaly?
That's very good. So it's you will see where it comes. So there is a choice here of plus or minus the Chern-Simons level, and this is the sign here. You will see where it comes from in field theory in 4 dimensions.
Okay, thanks.
Shalom, I have one question.
Yes.
So do you have any 6D explanation why we have SU3 global symmetry at the puncture?
6D, directly 6D without going to 5D.
Yeah.
It's an excellent question. I don't have an explanation.
Okay, good. Thank you.
Well, in fact, no, as you know, right? So in this particular case, you can ask whether this is the only puncture that you can have.
Mm-hmm. Yeah, right.
And I don't have even a proof of that. This is a puncture that you can have. In other cases, like in D-type conformal matter and so on, you can have various symmetries, punctures which have very, very different symmetries, and so on. And
so usually we don't have a clear explanation in 60.
Exactly. So in these cases where we know of these effects, we know of them because of Kim Young's and friends' work about the 5-dimensional reductions of those theories. And there are various, turning on various holonomies, you can get different types of 5D theories with different gauge groups. And then the explanation is always a 5D explanation. A direct 6D explanation, I don't know. And this will come actually in several minutes. This question will become more important. But thank you. It's a very good question, of course.
Schlomo, what is the role of Z2 twist here?
Okay, so you can ask why do you need the Z2 twist in this particular case, and you can match. Oh, sorry. You can match them. Okay, so as I mentioned, this minimal SU3 SCFT in 6 dimensions is described on its tensor branch by pure SU3 gauge theory. Okay, so you can try to compactify this theory and match the moduli spaces of the 6D theory and the 5D theory, and you need this twist for this matching to work.
What does where does Z2 act?
On the tensor branch, you have for example, you have this the adjoint field in in 6 dimensions, and it takes it to -1, like phi goes to -5. So it projects the trace phi cubed operator. Okay, it's in 6 dimensions. It's a complex conjugation.
That sounds like you're breaking SU3 down to SU2 or in some way.
Well, yeah, fine. Yeah, yes.
But your global symmetry is still SU3. So
no. This is again not to be confused with this SU3. This SU3 is a description of this theory in 6 dimensions. This is on a tensor branch. And you can take that theory on a tensor branch and discuss its properties. And then there is another question where you take this theory down to 5 dimensions and ask what is the effective 5-dimensional description. In this case, with some miracle that I don't understand, in very nice way, you get also an SU3 gauge theory description. However, there are other examples. For example, if you have an SO8 minimal SCFT in 6 dimensions and you do this reduction to 4 dimensions, sorry, to 5 dimensions, you get an SU4 gauge theory in 5 dimensions. So there is no a priori reason that these groups should be related.
I see. Thank you.
Okay.
Can I ask you a quick question?
Yes.
So if you put genus to be 0, then you get negative A and C.
Okay.
And so it means that you have non-unitary theories.
Okay, so genus 0 is this. This is an excellent question. Genus 0 is always a little bit special. So also genus 1 is special.
All right.
So when you get A and C, which are negative or some weird numbers, this can mean a lot of things. Well, one thing that it means that you probably get the A and C wrongly. That's not the correct answer. Okay. And what can happen? It can happen that the theory is gapped in 4 dimensions or whatever. It can happen that you have some accidental U1 symmetries. So you're just identifying certain R symmetry in 4 dimensions, but it is not a super conformal one. Okay, so you're computing some A and C through traces of R cubed and trace of R, but this is not a super conformal R symmetry.
I see. Okay.
So, but in general, on a sphere without flux, we don't really know what the 4-dimensional theories are. When we take a sphere with enough flux, the 4-dimensional theories actually become nice, and you can say something about them.
I see. Okay, thank you. Yeah.
So let me then quickly go over the same story for the E string. Again, if you take an E string with some holonomy on a circle, you get an SU2 gauge theory with an f equals 8 in 5 dimensions. And again, I believe Sakura has already discussed this yesterday. And again, we can do the same story. We can freeze this SU2 symmetry on the boundary with the proper boundary conditions. However, here we have also matter multiplets. So we need to choose some boundary conditions for them also. Okay. And again, there is a nice boundary conditions where you have here, in n=1 language on the boundary. On the 4-dimensional theory, you have 8 chiral multiplets, you have 8 hypermultiplets, which you can split into an octet of 2 octets of chiral fields, n=1 chiral fields, and you can give 8 of them Neumann boundary conditions and 8 of them Dirichlet boundary conditions. And there are certain choices involved, how you split the 16 chiral fields into an 8 and 8, and which ones you actually do give these boundary conditions. So if you have one puncture, all these choices are equivalent, but if you have different punctures, these choices become inequivalent. So the relative choices might matter. So all I want you to remember from this story is that the symmetry that you have, which is associated to the puncture for the E string, is SU2, and you have an octet of natural operators in the fundamental representation of SU2, which come from these fields that you have in 5 dimensions, and this will become important later on. Okay, so again, as in the minimal SU3 case, you can compute the anomalies with the punctures, and you get these results for A and C anomaly, and you have a puncture symmetry which is SU2. You can compute the trace R SU2 square anomaly, and which turns out to be equal to -1. Okay, something that was implicit in what I was saying, this R symmetry, you can ask, what is this R symmetry? And this R symmetry is the Cartan of the R symmetry, of the 6-dimensional R symmetry, which we inherit in all these compactifications. In the minimal SU3 conformal matter, there were no abelian symmetries. So that was the only R symmetry that we could have. But in this case, we have the E8 symmetry, and we might break this E8 symmetry to a smaller group by fluxes, and these boundary conditions at the punctures also break this E8 symmetry to a smaller group. So we might have a lot of U1 symmetries which can mix with this R symmetry to produce a superconformal R symmetry. So this is not the superconformal R symmetry necessarily. This is the one which is inherited from 6 dimensions. Okay, and since we have this E8 global symmetry, and we break it to some subgroup by fluxes and by boundary conditions, we can compute also various 't Hooft anomalies for all the relevant symmetries of these global symmetries that we can have here. And the details of these anomalies will depend on all the knobs and levers that we have. So I cannot write the general expression. It will take several pages. And in the paper with Hichol several years ago, we discussed at least a lot of these possibilities. So, but this needs to be mentioned. And again, importantly, once we will have U1 symmetries, we can mix them with the 6-dimensional R symmetry, and the superconformal R symmetry in general will be some mix of these. Okay. So now finally we come to the question, what are the 4D theories that you get in this compactification? Can we describe them directly in 4 dimensions? Is there a question?
Yeah, can I ask a question? Just
Sure.
For the boundary, do you mean the boundary is the boundary of the 5D theory?
That's right.
So, oh, I see. So it's a, okay, thank you.
So it's this, you see, so this is the Riemann surface on which you compactify. So you first, you keep the 5th dimension non-compact. You just look on the vicinity of this puncture, and you put a boundary in 5 dimensions. In the end, you will compactify also the 5th dimension when you go to 4D. But to understand the puncture, you make the analysis in 5 dimensions.
Thank you.
Okay, so now what are the theories in 4 dimensions? So we start with example 1 of the minimal SU3 SCFT, and we do exactly what we did yesterday when we looked for the conformal dual of the G2 SQCD. Okay, so we already have understood that, say, if you compactify on a closed Riemann surface, then the dimension of the gauge groups should be 32 times G minus 1, and dimension of representation should be 81 times G minus 1. Okay, and there is this natural interpretation of these numbers. Now we also have understood punctures, and actually the fact that the punctures are SU3 here fits very well with this natural interpretation of the of 32 as being 4 factors of SU3. So we can think of gluing these Riemann surfaces together along the punctures by undoing this effect of putting Dirichlet boundary conditions, so making these frozen SU3 symmetries associated to the puncture dynamical. So gauging these SU3 symmetries, so this fact fits well. Also, the fact that the cubic anomaly is of this SU3 is plus or minus 9, and the fact that trace R SU3 square is equal to minus 3/2 field fits very well with trifundamentals, that we need to build the theories using trifundamentals. So here are, we write these trifundamentals, and they will have these two notations. So if we have a trifundamental without any superpotential, I will just use this notation. And if we will also have trifundamentals where we turn on a generic baryonic superpotential, breaking this SU3, which rotates this triplet of bifundamentals of these two SU3s, and then I will denote this by this block. But now let us look on any one of these and compute the trace SU3 cubed anomaly of any one of these SU3s. Well, we have 9 fundamental fields, so we'll get anomaly which is plus or minus 9, depending on whether it is fundamentals or anti-fundamentals. So this is to Jay-Won's question before. There is this choice of whether you have plus or minus 9, depending on whether you take fundamentals or anti-fundamentals. Okay, this is where it comes in the 4-dimensional description. And also this anomaly, trace R SU3 squared, when you compute it, again, for this type of an SU3, it gives you exactly minus 3/2. Okay, so you have a half coming from SU3 square from fundamentals, then the R symmetry. Here we think of these fields as free fields, so the R symmetry is 2/3, you get 2/3 minus 1, and each such SU3 has 9 fields, so you get minus 3/2 anomaly. Okay, so we thus conjecture that, you know, to build the theories with which will result in these compactifications, we need to gauge SU3 symmetries, and the blocks that we need to use are these trifundamentals of matter. Okay, I didn't tell you what these trifundamentals correspond to in compactification. I just told you that these are natural blocks with which we can play this game of constructing 4D theories. And here are the results. You just play as we played yesterday, trying to construct a gauge theory which has all the right properties predicted, you know, in that case by this G2 SQCD, in this case by geometry. For example, if you look on compactification on genus 2 surfaces, you can find 2 theories that look very differently, but they they have all the right properties to describe this compactification. And again, this wiggly line is just 3 fields, a trifundamental with a baryonic superpotential. Okay, and if you want a 6 punctured sphere, you get such a theory, and ignore these numbers which are written here. If these are related to some computation of the conformal manifold of this theory that you can find in the notes, and you can actually construct using these blocks any 4-dimensional theory that you want. And the basic building block in this construction is this theory, which is a combination of 3 trifundamentals with a baryonic superpotential with 2 SU3 gaugings, which you can naturally associate to a 4-punctured sphere. And here it actually relates to Hitchell's question. This is a little bit funny theory, because if you will do the analysis of conformal manifold, as we did several times in these lectures, you will find that it's not enough to turn on this baryonic superpotential to actually explore the conformal manifold of this theory. Okay, so the claim that this is a 4-punctured sphere is actually more sophisticated. And this is related to Hitchell questions in the following way. You know, if we would have a nice 4-punctured sphere, okay, with where you glue 2-3 punctured spheres together, we could just decompose these 2-3 punctured spheres, these 4-punctured sphere into a 2-3 punctured spheres, and then we will get a nice puncture. But this puncture cannot be of the type that we encountered before. Remember that to get these punctures, we had to do this Z2 twist. Okay, but that means that the number of punctures that we can have is an even number of punctures here on the sphere. We cannot produce an odd number of such twisted punctures. The total twist should cancel out. So when we take this 4-punctured sphere and try to decompose it into 3-punctured sphere, in the middle, a new type of puncture should appear. Okay, but it doesn't have to be a simple gauging, or we don't know what it is. It's something else. Okay, and again, the detailed discussion of this effect you can find in the notes. Okay, but again, what I want to stress here, that these different theories that you get in 4 dimensions should be dual to each other. Okay, because they are just different pair of pence decompositions of the same surface. If you wish, in terms of this 4-punctured sphere, you either glue 2 pairs of punctures like that or like this, and get a theory which should correspond to the same Riemann surface. And this looks like a new type of a conformal duality. So here is a new duality that you discover in this way. Okay, so I want to make a more direct contact to what we discussed before. So let me do the following. So first of all, before doing some new operation, let me also quote what are the indices of these theories that we have constructed here. Okay, these are just Lagrangian theories, usual theories. You can compute their indices. In particular, when you compute these indices, you find that there are no relevant operators. And as I discussed, relevant operators you will, in these geometric constructions, you will typically obtain only when you have flux, when you compactify on closed Riemann surfaces. You have global symmetries and you have flux. Here, there are no relevant operators, which is consistent with our generic expectations. And also, the number of exactly marginal deformations is 3G minus 3 plus S. In particular, if you don't have punctures, it is 3G minus 3 is the thing that we have discussed in the beginning. Okay, so the spectrum of operators is again consistent with our generic expectations. Okay, so this is another check of this procedure. And now to make contact to the SU3 with the NF equals 9 that we discussed in great detail, I believe in lecture 2, we can do a new operation. In 4 dimensions, if you have an operator which is charged under some symmetry, a chiral operator, we can entertain giving a VEV to this operator. Okay, such a VEV will initiate a flow to a different SCFT, and in the process it breaks the symmetry under which this operator is charged. It turns out that this type of an operation has a geometrical meaning. It produces to you a new type of a puncture. You start with some type of a puncture and you produce a new type of puncture. Here you can do such a VEV. You have these operators which are charged under puncture SU3 symmetry. You can give them a VEV. This procedure actually breaks the symmetry completely, and you obtain a puncture which doesn't have any symmetry. Okay, why do you have a puncture which doesn't have any symmetry and not completely remove it? And the reason is again this twist. This twist needs to go around something. The twist is there, so you are left with a puncture which doesn't have any symmetry but has a twist around it. For example, if you do this procedure of giving a VEV to an operator to a 4-punctured sphere, you arrive at an SU3 SQCD with an F equals 9, just this theory. And this will correspond to a sphere with 2 SU3 punctures and 4 empty punctures. This is a sphere with 6 punctures, so it has a 3-dimensional conformal manifold. And if you go to lecture 2, you will find that when we analyze this SQCD and we insisted on preserving 2 SU3 symmetries, there was a 3D subspace of the conformal manifold which did that. And you can continue playing these games. For example, an SQCD with SU3 and the most generic baryonic superpotential will correspond to a 10-punctured sphere where these punctures are these empty punctures, punctures which have no symmetry associated to them. The conformal manifold that we found was 7-dimensional, exactly what we would expect from a sphere with 10 punctures. Okay.
Can I ask you one thing?
Yes.
So
Yes.
this looks slightly different from the old picture of class S, where if you close the punctures and you do not get like extra, but here, upon giving a web, you seems to create many punctures.
You just no. So in class S, there is a procedure like that. You start saying with maximal puncture, you start giving webs, and then you get other types of punctures, like smaller punctures in general, right? In the end, you always can completely close a puncture. You give some web, which completely removes the puncture. But here, you should think of this puncture as having a twist around it. And these operations of the giving a web somehow never remove this twist. So in the end, you have a puncture which has no symmetry, but you have still something. You know, in class S, there are these other types of punctures, irregular punctures and so on, which can have such properties also, like they have no symmetry associated to them. So if you wish, this would be an analog of such a puncture.
I mean, even for the there are like twisted punctures in class S where you cannot really completely close by Higgs.
Exactly.
So I think this is
Exactly.
similar to that, but it doesn't.
Exactly.
But still, it's not like you get more punctures out of Higgs closing one.
Oh, you're asking, okay. You're asking why we get here more punctures?
Yes.
That I put under the rug. Yes, this is an excellent question. Since you ask, okay, I don't have too much time to discuss it, but it's a very interesting effect. It's a completely different effect. So I skipped here several steps, but actually the statement here is very interesting, and it also has a class S analog. The statement is like that you have here these maximal punctures, the SU3 punctures, and actually, you know, as is clear from our discussion, for example, just take this statement as given, okay? What you have this theory, but you have also, it has this 3-dimensional conformal manifold on which these two SU3 symmetries are preserved, but now you can turn on more generic baryonic superpotential and go to explore a bigger conformal manifold. So the statement is that what happens when you explore this conformal manifold, each of these maximal punctures can split into a triplet of these funny punctures, of these empty punctures. Okay, so going on this conformal manifold, you break the symmetry and one puncture splits into 3. And this has class S analogs. It was discussed by Jacques Dissler and Yuji Tachikawa and friends, again, in twisted compactifications. They call it atypical degeneration. Okay. Usually when you split punctures, you have kind of, you know, some gauge. Well, let me not go into that. But there is such an effect also in class S where punctures of certain types can collide and create a different type of a puncture. Okay.
I see.
But yeah, this is a very interesting aspect of this story, but I don't have time to go into it in detail.
All right.
Okay.
Thank you.
Okay. So this was the story of SU3, minimal SCFT, and we made the connection to SU3 with an F equals 9. In that case, again, I stress that we have now a geometric understanding of this funny 7-dimensional conformal manifold of that theorem. So now let us go to our second example, to E string. And again, we just repeat the story. We know what the dimension of the group should be if there is a conformal dual. What is the dimension of the representation? Here, the story seems a little bit more funny. Again, the natural interpretation of this 16 is in terms of SU3 groups, but we discussed that the punctures are SU2 groups. Okay, so these SU3s cannot be gluings of the punctures. This is something else. Okay, but let us ignore for a time being this information about the punctures and just try to build theories which have these anomalies and other properties which match with this string compactification. And it's very easy to build such a theory. For example, a theory which corresponds to genus G surface, which has these properties, is this nice looking circular quiver, where we have 2G minus 2 SU3 gauge groups. Okay, and we have naively an SU9 global symmetry group. We can again compute, for example, the index of this theory. You can easily convince yourself that this theory doesn't have any relevant operators. Okay, this theory, each gauge node has 9 flavors, so it is a conformal theory. Doesn't flow anywhere. So the R charges of all the fields are 2/3, as we assumed when doing this computation. And you cannot just build, you know, R charge 4/3, for example, gauge invariant operators. You can, however, build a lot of marginal operators from all the baryons. For example, there will be an operator which will go like that, which will be in 80 plus 1 representation of this SU9 group. There will be baryonic operators like this, which will be in 84 or 84 bar representation of SU9. And it so happens that all the marginal operators are either singlets of this SU9, or they always combine into 84 bar plus 84 plus 80, which is a decomposition of the joint representation of E8 under, into SU9 representations. SU9 is a maximum subgroup of E8, and that's how it decomposes. So again, it's exactly what we expect from the conformal manifold. 3G minus 3 plus 248 times G minus 1, where this is not just a number, it is actually a character of the joint of E8. Okay. And another thing that you can do, you can easily compute the trace R times SU9 squared anomaly of this symmetry. And you find that this anomaly is equal to minus G minus 1. And remember, I mentioned that trace R E8 squared should be minus G minus 1, minus of G minus 1. And the embedding index of SU9 inside E8 is 1. So it has to be the same number. And we find that the Dist-Hooft anomaly also matches. So the claim is that this theory corresponds to this compactification, and in particular, somewhere on its conformal manifold has a locus where we have an E8 symmetry. Okay, and the precise statement is that the Cartan generators of this SU9 that you see here, they become the Cartan generators exactly of that E8, and that's a non-trivial statement of emergence of symmetry, now not in the flow, but on the conformal manifold. Okay, and this we obtain from this geometric type of a construction. Okay, any questions about this? Okay, so next you can ask, okay, we found here a class of theories which correspond to genus G, but is it the only, are these only, you can find only these circular quivers, or there are other types of theories that you can find? So here is an example of genus 2. So this is actually this circular quiver of the previous slide in case of G equals 2. I just drawn this differently. I did not to write it in exactly the same way. I should have written this triangle, but here I just did not identify these SU9s. So there is this theory that you can obtain, and in fact you can build a completely different theory, which is written here, which has each SU3 has 10 fundamentals, 3 anti-fundamentals, and a 6-dimensional representation coupled to it. And it actually has exactly the same properties as this theory. The anomalies are the same. You compute the index, it is the same. These theories are dual to each other. They have they are conformal dual to each other. They have all the same properties. And actually, there is a nice interpretation of this duality. Look, when you can think of this kind of way of writing a quiver as associated to this pair of pens decomposition of the Riemann surface, where this one is this pair of pens decomposition. And the point is that if you have, we are used to have bifundamental starting from a gauge node and ending on the same gauge node, producing an adjoint plus a singlet. But if we take a field which is like in fundamental times a fundamental, we will produce a symmetric representation, which is here is a 6, and the anti-fundamental. So if we have here a 9, this will become a 10, and we will have another symmetric, the 6-dimensional representation. So this picture just tells us that there should be a way to understand these quivers that we have obtained by as gluings of three-punctured sphere by cutting in some way these lines, breaking these lines and combining them together in different ways. Okay, so we should somehow understand how to do that. Okay, and here comes this fact that actually the puncture symmetry that was associated to these pairs of points decomposition was not SU3, but it was actually SU2. So a way to do this breaking is to seek for somehow to introduce here an SU2 gauge symmetry in the middle, and it is very easy to do, again with a very simple Seiberg duality which we discussed a couple of lectures ago. Remember that if you have SU2 with three flavors, it is just given by this Wezumino model. Okay, you have these two SU3 symmetries, and this is the U1 baryon symmetry, and here you have the two baryons and you have the mesons in this of this theory coupled through a superpotential. And now look at this quiver. This is again this type of a quiver with a superpotential that now I introduced, and it is built from such triangles. Okay, so we can take each such triangle and exchange it with this type of a node. Okay, this is just using Seiberg duality. The flow is actually the opposite way. If you have such a theory, the RG flow will be to here. But here we are trying to decompose this quiver into SU2 gaugings. So when we take one triangle, this 9 becomes an 8, and we add an SU2 gauge node here. Then we do this operation again. The 8 becomes a 7, and we have another SU2. And then the third one, we break to, we have these 3 SU2 nodes, and this 7 becomes a 6 here. Okay, so this is exactly looks like what we want. We want, three SU2 gauge groups, which are connecting two trinions together. And what is it? Each trinion looks like, each three-punctured sphere looks like. It looks like an SU3 gauge theory with 6 flavors. Okay, so this is how you decompose this surface. So this is my kind of almost the last point. So the three-punctured spheres of these E-string theories are extremely simple. There are just SU3 SQCDs in the middle of the conformal window. But you need to think about these theories in a little bit funny way. So you have an SU6 times SU6 global symmetry rotating the quarks and the atomic quarks. You split one of the SU6 into these 3 SU2s, which you associated to the 3 punctures. And then the remaining symmetry, the SU6 and the 3 U1s that you get, one of them is U1 baryonic, and the other 2 are the U1s which you get by splitting SU6 to 3 SU2s. This is a rank 8 symmetry, which is actually a subgroup of E8. Okay, and again, you can compute various anomalies that we have quoted before for trace R and this SU2 puncture symmetry, and you get exactly the numbers that you expect for from compactifications and from this 5-dimensional analysis. Now, another important thing is that each one of these SU2s has a natural octet of operators in the fundamental representation of each SU2. So 6 of these are the mesons, and 2 of these are the baryons. So take this field and twice this field, or this field and twice this field. This is another baryon. And all these baryons and these mesons have the same 6-dimensional R charge, and they naturally build these octets of operators that we have discussed that we should associate to each type of a puncture. Now, this Riemann surface, actually, this compactification, this theory, should be associated to compactification with the flux when you analyze it in detail. Remember that when we obtain these types of anomalies from which we deduce this dimension of the group and dimension of representation, we didn't turn on a flux. But what actually happens here when we break these two, this genus 2 surface into 2 3-punctured spheres, we decompose it into a sphere with certain flux F and flux minus F, such that the total flux is 0, but each one of the components has some value of the flux. So when you do this analysis of various Hooft anomalies for various symmetries that you have here, you arrive at the conclusion that there is actually a half a unit of flux that you need to associate to this three-puncture sphere, which breaks E8 down to E7 times U1. Okay, and now the moment you have this three-puncture sphere, you can build any Riemann surface that you want by gluing these spheres together and closing punctures in the same way as we did for the minimal SU3. So any questions about that? And if not, I will. I have 2 more pages and I will finish.
So is there any relation between this, the three-puncture sphere and the TN theory in class S?
Exactly. This is the analog of TN theory for the E string, if you wish. So TN theory is the theory corresponding to a compactification on a three-punctured sphere of certain 2,0 theory. Okay. This SQCD is a compactification on a three-punctured sphere with a certain value of flux of the rank 1 E string theory.
I see.
But in this case, the theory is completely Lagrangian. In a sense, it's one of the simplest theories that you can write. Okay.
Yeah.
Okay.
So
yes.
So can you match the conformal manifold of this three-puncture sphere theory from geometry?
Oh, that's a good, excellent question. So this is again related to the fact that for small compactifications, there can be features which are not explained by geometry. Okay, so these red numbers that I written here are R-symmetry assignments to various fields. These are not the superconformal R-symmetry assignments. These are R-symmetry assignments which match the 6D R-symmetry. The superconformal R-symmetry is 1/2 for all the fields. So you can build actually a big conformal manifold here. It doesn't have a 6D interpretation. Okay. At least I don't know of any.
So what is the interpretation of that conformal manifold? And I mean,
what is the explanation?
Yes, that this is no analog in 6D because this is
well, yes. 6D. As I mentioned before, there are other, like this is, if you wish, this is a compactification on a small surface with small value of flux, and some other operators, and not just the stress energy tensor and conserved current in 6 dimensions might contribute to it. So it might be that there are some surface operators that give rise to this exactly marginal deformations. There might be some local operators which are other than the ones I mentioned, which give rise to that. That would be very interesting to understand. But this is a non-generic feature. If you will go to start building from this surface a generic, from these theories, a generic surface, the conformal manifold will be as you expect from 6 dimensions. So when you grow a surface, this small effects disappear. You have analogs of this also in class S of these types. For small compactification, sometimes some accidental symmetries appear. For example, if you take 2 trinions of SU2, try like in A1 type 2,0 compactifications and build a genus 2 surface, you have an accidental symmetry, which, as far as I know, at least I don't know of a geometric explanation of it. So there are certain accidents like that it will be nice to understand, from 6D, but they probably have to do something with very fine details of these compactifications. Yeah, but this is a very interesting to understand.
So in the 6D, when you compactify on genus 1 fiber Calabi-Yau manifold instead of elliptic fiber Calabi-Yau manifold, as E string does, you in principle will have some similar theory with the same global symmetry like here.
Like you want to compactify on genus 1?
Yeah, we compactify, the theory to on genus 1 fiber Calabi-Yau manifold with multi-sections.
So
and the
let me-
multi-section plays a role of the like the U1 to the cubic in the slides, and the remaining symmetry would be as U6 times U1 3. I think it's possible to have this Calabi-Yau manifold, and the resulting 4D theory has n equals 2 supersymmetry, but here is n equals 1, right?
That's right. So what you want to do is to compactify on a torus.
Right,
Just
instead
it?
of the genus 2 curve, right?
Right. So I didn't mention it, but if you do that and don't turn any flux, the statement is, the claim is that you get what is called the E8 Minahan-Nemeshansky theory,
Right. And
which
if you
is an equal to theory. But again, as I mentioned, genus 2 and genus 1 are a bit special. You can say various things, but the analysis is less generic.
Oh, I see.
Okay. You can
So
also
in-
compactify on a torus with flux, and then you will break this EA to some subgroups. But without flux, you preserve all the supersymmetries because the space is flat, and you get some n equal to theory. Okay.
All right, thank you. So may I understand that your process here, if we focus on a genus 1 Riemann surface, the 4D series still has a n equals 2 supersymmetry.
Right. So actually, you cannot get from this construction this torus that you want without any flux. So I mentioned that you can build any surface but this, in a sense, because this surface is a very singular construction. So you can you cannot build it. You see, you can build, for example, a torus with punctures by gluing these guys together. And then you can try to close punctures to obtain a torus without a flux, but it is a singular procedure. The flow becomes funny. Okay. So
Right,
compactifications on tori without flux are very special.
Okay, thank you.
You say that you can build arbitrary, like you can build this three puncture sphere with arbitrary choice of flux. Is that right?
No, yes. Once you have one choice of flux, you can do whatever you want. Because yes.
Yeah, that sounds like you can build an infinite set of dualities for.
Of course, yeah. There are enormous numbers of dualities that you can build. Some of them are very simple. Some of them are actually generalizations of known dualities. But I don't have time to go into it. But let me just mention, since you asked, there is this dualities for SU2 with 8 fundamentals. So there is that we have seen, like there is a Seiberg duality, but also there is this interligator-Puyo duality, where you don't just flip mesons, but also flip baryons. So you can ask, what is the generalization of that duality to SUN? There is a generalization to USP2N, which is well known, but to SUN, it is not known. But actually, by generalizing this picture, you can, like the claim is that if you have a 4-punctured sphere here, it is a natural, the pair of pens decomposition of this 4-punctured sphere is a natural generalization of interligator-Puyo duality. To see that, I will need to do, to show that, I will need to do a lot of things. So, but let me leave it as a
maybe we let first Schlomo end the talk, and then we can have some further questions. Where perhaps you can.
Okay. So let me just, I'm basically summarizing what we have done here. So let me, with this E-string example, just emphasize what we have achieved here. So we started from this E-string theory. We defined it, we deformed it by putting it on a Riemann surface with flux, and we flown to some theory in 4 dimensions. And we found for each of these choices, except for the choice of torus with no flux, we can find a 4-dimensional theory which either directly describes this theory, it's a conformal dual to it, or an IR dual to it. Okay, so it's if you wish, this is this example of IR dualities across dimensions. We have a 6D theory deformed by some deformations, and which is exactly flows to exactly the same fixed point as a collection of 4D theories. And as Jaewon mentioned, various ways of combining these 4D theories together so that we will produce the same surface will give us a lot of different IR dualities and conformal dualities, as we have seen, directly in 4 dimensions. And the explanations of these dualities is through this geometry. You build the same geometry, you need to have the same fixed point if this story is consistent, so you need to get dualities. Okay, so before I end, this is my last page. We had this very neat example of SU2 gauge theory with 8 fundamentals, which had an E6 symmetry times U1, which we analyzed in detail. So actually, this type of a theory you can obtain in these constructions by looking on a torus with some value of flux, a flux which breaks E8 to E6 times SU2 times U1. In fact, this particular theory, which you would get here, we discussed with Hichol and friends already 3 years ago in a completely different construction, but you can also obtain it by from these building blocks. And then if you deform this theory that you obtain on this compactification with some relevant deformation, which breaks only this SU2 and not E6, this is exactly the theory you would obtain. So this is 6 times U1 emergence of symmetry that we have discussed, actually, in a way, follows from these geometric considerations that we had here. From this observation that this is a trinion, from understanding how you close punctures and so on, you can obtain that this theory has to have the C6 emergent symmetries. So this also has a geometric explanation. So there are many interesting questions to ask. Let me just mention 2 obvious ones. So one, from this discussion, you can ask, do all emergent phenomena and dualities in 4 dimensions come from some kind of a geometric consideration? Okay. By now, we know, most of the dualities, I would say, that were known can be explained geometrically, not all of them. And many new dualities and emergence of symmetries were obtained from geometrical considerations. So that's one big question. Another question is, do all CFTs or QFTs in 4 dimensions that you can build in such geometric way, let me call them geometric QFTs in 4 dimensions, do all of them have a description directly in 4D? This is a question which can be rephrased, are there non-Lagrangian theories in 4 dimensions? Okay. By now, we know more and more compactifications can be described by directly flowing from 4 dimensions. So is it true that any such geometric construction has an IR dual directly in 4 dimensions? Or there is some abstraction to this that we don't know of? Okay. So, and another thing I want to mention is that in many places in this discussion, emergent symmetries appeared. Emergent symmetries emerged. Okay, and this play an extremely important role in various types of constructions. And I think there is a lot to be done to understand what you can do with these emergent symmetries and what can you build with these emergent symmetries and how to think about them. So with this, I want to finish. Thank you.
Yeah, thank you very much, Schlomo. Maybe I have one question which I wanted to ask, namely in the usual class S construction of this, there is also this 4D, 2D correspondence where you can put conformal blocks on the Riemann surface and compare with the partition functions of the 4D theory. There is an analogous statement here, or right?
I don't know. You see, the most obvious way how you go about this in 4 dimensions in n equals 2 is through this S4 partition function and AGT types of correspondence. But S4 partition function by itself for this n equal 1 theories is ill-defined.
But you have the index, right?
The index is a different thing. The index I will mention. So, but the analog of AGT, I don't know if there is one. It's not that obvious that there is one. I would, in a sense, be a little bit surprised if there is one, but maybe there is another way to think about it, and not through S4 types of partition function, and then you can find it. This has not been done. Eli Pomoni had done some attempts into that direction in other compactifications, where you take M5 branes on ZK orbifolds, which are basically in certain cases, not always, just orbifolds of the class S theories. And then she tried to discuss some of these questions. But in general, I don't know of anything. But the index, like the fact that the index, a superconformal index of these geometric 4D theories is related to some 2D topological quantum field theories, is generalizable. There is a statement. So in the case of 2,0 compactifications, this topological theory you get in 2 dimensions is related to what is called Ruijsenaar-Schneider integrable model. Okay. In the case of E-string, you can derive it, the integrable model, and it also has a name. It's called the Van Diechen model. Van Diechen model is associated to BCN BCN root system. So the BC1 Van Diechen model corresponds to rank 1 E-string. It has 8 parameters, the BC1 Van Diechen model. And it's not surprising. These 8 parameters are the fugacities for the E8 symmetry. The BCN generalization for n bigger than 1 has 9 parameters, and it is naturally to be associated to higher rank E-string theories, where the global symmetry is E8 times SU2. This SU2 doesn't act on anything for the rank 1. Okay, so these are the integrable models. And for each such compactification, you can ask what is the related integrable model or TQFT, and you can find it. Sometimes it has a name, sometimes it doesn't have a name. But that certainly has a generalization. The AGT type of correspondence to a CFT in 2 dimensions, I don't know. I would be surprised, but there might be a way to think about it.